Okay, so now that I've established the why we're doing what we're doing, and I will now address the how. How do we write our equation? Once we know that we want the integral of acceleration, how do I exactly set that up? So, just one thing for the physics students, please be aware that your formulas from physics cannot be used. So you'll have some formulas about the connection between acceleration and maybe velocity, and actually you can't use those in the maths course, so just be aware of that. And for those students that don't do physics, you just stay, obviously you're probably not aware of those formulas, and so you won't be using them or won't be wanting to use them. So what are these definite integrals going to look like? Well, so what we have now is a situation where we can set up an integral, and based on, I guess, the wording of the question, if we were taking the integral of the velocity function from time is 1 to time is 2, for example, then what we're actually getting is the change in displacement. So we know that the integral of velocity is displacement, and if we're going over a period of time, which a definite integral allows us to do, then that the consequence of that is that we're getting a change in displacement. If we take the integral of acceleration, so we know that integrating acceleration takes us back to velocity, and we can do that from time 1 to time 2, we're getting the change in velocity. So should you get a question that asks for a change in displacement, a change in velocity, then this is how you set up your integrals. They're definite integrals. It's probably not the most common sort of question. The most common sort of question will be more or less asking you about instantaneous velocity at an instant, and you will need to integrate acceleration to get an expression for velocity, and then once you've got your expression for velocity, then you can sub in a value of t to find the velocity at an instant. So I'm just trying to distinguish between questions where you're asked for a change in displacement or a change in velocity, as opposed to instantaneous displacement where you're displaced at an instant. And of course, if you ask that, you sub into your displacement a function. Instantaneous velocity, you sub into your velocity function. Now, hopefully I haven't made that more complicated than it needs to be, or that it actually is. Anyway, as we work through an example, hopefully it'll become clearer. So let's have a look at this example, and like I've been saying, even in the introduction video, it's all about the words, and it's about focusing on how we can interpret mathematically the worded information that's given. So let's have a look at this one. A particle is moving so that its velocity t seconds after time is 0 is v equals 2t minus 2 meters per second. The units really will just always be, for velocity, they'll be meters per second or centimeters or millimeters, whatever, per second usually. Acceleration will be meters per second squared. Now, the fact that it'll have a squared on it doesn't mean we need to do anything. It's just how you measure acceleration, and displacement will just be meters, because that makes sense. The displacement is so many meters away. some students think that the way that the unit is written has some impact on the equation, and I just need to tell you that no, that is not the case. This is quite a nice question because you're actually given the expression for velocity. Now, knowing that you've sort of got the middle of the three expressions, you could probably already be thinking, okay, well, to go to acceleration, should the question ask that, I would differentiate. To go back to a displacement, given velocity, I would integrate. However, it goes on and gives you a little bit more information in that it says initially. Now remember, initially is a word that you really must be able to write down something mathematical as a result of reading that word, and we know that that is when t is equal to naught. Now that's the information contained within that word. So when t is equal to naught, it is, well, we're talking about the particle, it is at x is equal to 1. Well, that's great. We know that when t is equal to naught, displacement is 1. I will pause the video and write up just that amount of information that I can get out of the introduction to the question. So what I've done is I've just, as you can see, I've just taken that equation out of the information given and stated it here and interpreted the second sentence initially, when t is equal to naught, x is equal to 1. And we try to think about, well, we're forced to think about the word in order to be able to write the mathematical statement, t equals naught, and just think about that. So it's saying that at the beginning, if I was talking about the particle moving with, and here is naught, so I would say the particle starts here. This is time is equal to naught. This is the start. The particle is here at 1 at the start. Okay. What's A asking? It says, oh, well, it's telling you what to do. Integrate, substituting the initial conditions to show that x is this. So it's actually nicely stepping you through what you actually have to do, and I wouldn't expect that every question will be that kind. So we're going to integrate the velocity statement because that gets me back to displacement. Whoops. So I know that displacement is equal to the integral of velocity with respect to time. So displacement would be the integral of my velocity. I've stated that here, which is 2t minus 2 with respect to time. Now this is an indefinite. This question's not asking us about the change in displacement. It's an indefinite integral. So t squared, integrating now, we'll get t squared minus 2t plus a constant. It's at this point that I need to use this information here so that I can find the value of the constant. So we can see that here there is no constant. Displacement is all in terms of time and a number. So that's, I've created an expression for displacement in terms of time but some other constant, and now I can't have that constant because you can see up here there's no constant. And we don't want an expression for displacement with two variables, this constant and, well, it wouldn't be a variable but a number. We want that constant basically to be a value. So what did we know? We knew that we were given that x would be 1, so in this spot I'm going to put 1, when t is naught. And this is what I was saying in a previous video, that subbing t equal to naught, it creates a really simple equation, and we can say that therefore c is equal to 1. So now I can go back to here and complete my expression for displacement as t squared minus 2t plus 1, which hopefully you recognise as a perfect square, and because that's square the first, twice the product of the two square the last, and so I can write, or I've been able to show that the displacement is this expression. t minus 1 all squared. So in B it says find when, what's your understanding of when? Hopefully it is find t. When a question says find when, that means you're finding the t. Find when the particle is at the origin. The particle is at the origin. What does that mean? Well, if it's at the origin, we know its displacement. And we know its location. So from that word, or from that statement, the particle is at the origin, mathematically I can interpret that as x is equal to 0. So find when, so find t when x is equal to 0, and also find the velocity. So I'll be finding v as well once I've got the value of t. Remember, we were given an expression for velocity, so we don't have to, we won't need to find that. We were given velocity. We found our displacement. It's just we've got to find what value of t to sub into here. Okay, so using our expression for our connection between these two, find t when x is 0, my equation connecting those is this x equals t minus 1 all squared. I want to solve for t. That's what find t means. I'm solving for t. And I know that in that x spot I can put a 0. So you can see there that that's what I've done. In order for this to equal 0, there's only one value, t is equal to 1. And completing the requirement for B, which was to find V as well, if t is equal to 1, then we get, using our expression for V that was given, 2 times 1 minus 2 is actually 0. Okay, so what have we found? We know that the particle, in summary, what do we know? The particle was originally at 1. After 1 second, we know that the particle is now at the origin, at x is 0. So if it started here, we know it's going in this direction, and it took 1 second for it to get, we took 1 second for it to get back to the origin. And what happened there? What actually happened after 1 second? Well, we can see here that the velocity was 0. What's your understanding of velocity 0? The particle actually stopped. The velocity is 0. That means the particle is stationary. See, and if we can actually understand what our calculation and what situation is this actual example is about, and every situation will be different, then it will assist us to answer the subsequent questions, because C goes on to say, explain why the particle is never on the negative side of the origin, and differentiate to find the acceleration and show that it is a constant. I'm going to have to pause the video because I'm running out of time, and I'll write that up, and hopefully you have time to come back and talk about it. Okay, very, very quickly, if we look at, so C is asking to explain why the particle is never on the negative side of the origin. So it's talking about its displacement. So we're going to focus on the displacement equation. The displacement equation has a squared. Anything squared must be positive. So therefore the particle can never be, the displacement can never be a negative number, and hence it can never be on the negative side. D then says differentiate to show that it's a constant. Well, you differentiate velocity. Differentiating velocity, you get 2. So the particle is always has a positive force on it after time is 0. I don't know what happened initially, that the particle was heading in a negative direction, but it now always has a positive force on it. And I'll stop the video.